Welcome to the Explainer. You know, inside every single piece of modern electronics, your phone, your car, a satellite zipping through space, there's a tiny, vibrating heart. It's an oscillator, and its only job is to keep perfect time. But there's this invisible force, this constant pressure trying to throw it off. Today we're diving into why the battle for an oscillator's stability is one of the most critical fights in all of engineering. So what is that invisible force? Well, it's a tiny, relentless variation in timing. Engineers have a name for it. They call it jitter, or instability, and it is the absolute nemesis of every high-speed digital system out there. This is what messes up signals, creates errors, and ultimately, it's what makes our technology fail. Understanding it, and more importantly, fighting it, is what this is all about. Okay, before we get any deeper, we've got to be really clear about two key ideas: accuracy and stability. They sound similar, but they're not. Think of accuracy like this. Someone tells you the exact time from a perfect atomic clock. A lot of systems get that perfect time signal from an outside source. But stability? That's totally different. Stability is the device's own internal ability to hold on to that time, to keep ticking consistently, second after second, without wavering. And for most electronics, that internal stability is what really, truly dictates performance. All right, so if you're going to fight this instability, you first have to be able to see it, right? You have to measure it. And that meant engineers had to invent tools that could see timing errors smaller than a billionth of a second. The first tool we're going to look at measures something called phase noise. Now, imagine a perfect signal is like a single, crystal clear musical note. Phase noise is like a low-level static, or a fuzziness that surrounds that note, just blurring its clarity. And that fuzz isn't just noise. It's actually energy that's leaking away from the frequency you want. And as you'll see, it can cause absolute chaos in things like high-speed communications. So what does all that fuzz and static actually do in the real world? Well, it means more errors in your data transfers. It drops your Wi-Fi quality. For something like a radar system, it could totally hide a faint target in just a sea of noise. It really degrades every single signal it touches. So the takeaway here is pretty simple. The cleaner the signal, meaning the lower the phase noise, the better your device is going to perform. Period. Now, while phase noise is looking at instability in the moment, like a snapshot, our next tool, the Allen deviation, or ADEV, looks at it over time. Think of it like a diagnostic chart, something that tracks an oscillator's health. By watching how the frequency wanders over seconds, minutes, or even days, ADEV can tell you exactly what type of noise is causing the problem. It's a super powerful diagnostic tool. An ADEV plot basically tells a story in 3 parts. Over here, in the short term, you see the stability is dominated by just random white noise, kind of like the background hiss on an old record. Then, as we observe for a little longer, we hit this flat part, the noise floor. This reveals the oscillator's deep-down inherent flicker noise, a much more stubborn instability. And then, if we wait long enough, the curve often starts to creep back up. And that shows the unmistakable signature of physical aging and long-term drift. So we can measure instability, we know what it looks like on a chart, but what's actually causing it? Let's meet the 2 main villains that are constantly working to throw our oscillators off frequency. And this quote says it all, really. The number one enemy of stability is heat. As a quartz crystal physically expands or contracts with temperature, its frequency changes. But it's actually worse than that. The crystal doesn't even go back to the same frequency when it cools down. It's this really frustrating effect called hysteresis. Every single temperature cycle leaves a tiny, permanent scar on its performance. The second major culprit is what we call aging, or drift. This is a slow, irreversible, permanent change in the oscillator's frequency that just happens over months and years. You can think of it like this slow, inevitable creep away from its original frequency, and it affects every single crystal oscillator ever made. If you zoom in to the microscopic level, aging is basically death by 1,000 cuts. Tiny little contaminants left over from manufacturing can actually land on the crystal, changing its mass and its frequency. The internal structures that hold the crystal can slowly relax their grip, changing the physical stress. Even impurities that were already inside the crystal can start to migrate across its surface over time. Each one of these is just a slow, constant attack on the oscillator's stability. Now, beyond heat and time, there are other, more sudden forces that can really knock an oscillator off its game. So let's take a look at the accomplices. Yeah, the list of accomplices is pretty long. A sudden physical shock or even just constant vibration can jolt the frequency. On the electrical side, if you push too much power through the crystal, you can permanently damage it, while a bad circuit design might starve it of the power it needs. Even things like the quality of your power supply or subtle stuff like exposure to light or magnetic fields, they can all add their own little bit of noise to the mix. So the situation might sound a little bleak, right? But this is where engineering comes to the rescue. This is where things get really clever. Let's see how we actually fight back against all these different sources of instability. So the engineering solution isn't just one size fits all. It's a whole series of trade-offs. At the base level, you've got your standard crystal oscillator, the EXO. For better performance, you can move up to a temperature-compensated one, a TC-EXO. And then for the absolute ultimate in precision, you've got the oven-controlled OC-EXO. Each step up gives you this huge boost in stability, but, and you can see it right there, it comes at a cost. It uses more power. The TCXO is really the smart solution to the heat problem. It has a built-in sensor that's constantly measuring the temperature, and as it sees a change, a dedicated circuit intelligently adjusts the electronics, actively pulling the frequency right back on target. It's in a constant fight against temperature drift, in real time. And what about the OCXO? Well, this one is the brute force, high-performance champion. It literally puts the quartz crystal inside its own tiny insulated oven. This oven maintains a perfectly constant temperature, which basically eliminates temperature as a source of instability altogether. It's pretty much the ultimate in stability engineering. And beyond these big solutions, engineers use a ton of other clever tricks. They'll burn in new crystals, aging them really fast in a controlled way to get past the most unstable part of their life. They use perfect airtight seals to keep those microscopic contaminants out, and even simple circuit design choices, like blocking certain voltages, can prevent internal damage and really boost that long-term reliability. So, what's the payoff for all this engineering? Well, the results are just dramatic. Simply compensating for temperature with a TCXO makes an oscillator about 20 times more stable, but putting it in an oven? The OCXO delivers over 1,000-fold improvement. I mean, that's the difference between a good signal and a nearly perfect one. So at the end of the day, this whole battle for perfect, stable timing is what makes our connected world even possible. But as we push towards even smaller, faster technologies, things like MEMS, oscillators, and even chip-scale atomic clocks, it really makes you wonder, is this decades-long fight for stability finally over? Or is it actually just beginning?